morning. In today's class, we first do something like 3 illustrative examples on atmospheric dispersion so that we can follow it in the context of explosion and safety. And once that's over, we get into quantification of damages. Let's see, let's start with an example. Let's take the example of the explosion at Port Hudson in Missouri. This happened, we said, on something like December 7, 1970, at night around 10:25 p.m. night. Okay. December being a cold month, it was extremely cold that evening or that night. And what happened in this incident is you have a pipeline conveying liquid propane, which sort of burst. The propane was at high pressure, or around 65 bar. It opened at one of the welding joints, and you had a huge fountain of liquid propane. And liquid propane is, when at a high pressure, is stored as a liquid, and this is at ambient temperature. But at the ambient pressure of 1 atmosphere, it boils at something like minus 43 degrees centigrade, and therefore it immediately flashes into vapor. That flashing into vapor absorbs the latent heat, and you have a fog of propane vapor which is formed. In addition to the fog of propane vapor, it also entrains some air, and therefore you have something like a mixture of propane air which is being formed at the zone wherein the burst takes place. We had also told ourselves earlier that this particular pipeline was on the side of a hill, and there was not many buildings around it, but at a place, downwind, that particular day the wind at night was around 2.7 meters per second wind, and the wind was downhill, and at a place something like 330 meters away, after something like almost some 10-15 minutes, the propane air mixture, that is the propane which is gushing out, gets drifted by the wind in the atmosphere, and it keeps getting diluted. Let's look at the dispersion of it, and it enters into a warehouse. In the warehouse, what happened is it housed some refrigeration units, and some of the hot motor or the control motors of the refrigeration unit ignite the propane air mixture. Now we want to look at the dispersion of propane downhill along the wind, and 2 things we realize. One is it's the night time. We are also told that the sky is fairly clear, which means we say that the cloud cover above this particular area, that is the cloud what is available, is something on the low side. The temperatures are around minus 1 to 0 degrees centigrade, cold night. Therefore we have something like in the atmosphere, you have atmospheric inversion, that means positive temperature gradient above the surface, and we looked at atmosphere in terms of its unstability, unstable atmosphere wherein anything gets dispersed away. On a cold night wherein the atmosphere is stable, you could have extremely stable atmosphere, you could have somewhat moderately stable, you could have something which is very weakly stable. And therefore, let's look at this Pascal's qualification. I show it in the slide over here. We are talking of wind speed of the order of 2 to 3, that is around 2.7 meters per second. We are talking of a night wherein the cloud cover is very small. Therefore, the Pascal's classification of the atmospheric stability is F. Therefore, we recognize, therefore we tell that, well, the condition of atmosphere that night wherein the leak happened is F, point 1. Point 2, the type of ignition energies which a hot source, like something like a hot compressor or a control unit of a refrigeration can give, is quite small. Therefore, we expect maybe the propane air mixture which got drifted and formed, and in this particular building, should have been near to stoichiometric. Why should it be near to stoichiometric? Let's say if I consider propane has a lean flammability limit around, let us say, 2.2 volume by volume, percentage volume of propane and volume of the mixture, upper around 9.5 to 10 percentage volume by volume, and in between those two, if I were to plot, let us say, the minimum ignition energy versus, I say, percentage volume by volume, well, this corresponds to something like 2.2 to 2.5. This is the lean limit of flammability. Upper limit of flammability, well, the curve for the ignition energy would be, minimum ignition energy would be minimum around stoichiometric, and it will go up over here. Therefore, let us see what is the type of stoichiometric mixture which should have formed here, otherwise it could not have ignited, because we do not have a good igniter or a strong igniter, and therefore, let us work it out. Let us say for propane air mixture, I am talking of propane C3H8 plus oxygen. 1 mole of oxygen in air carries 3.76 moles of nitrogen. And for stoichiometric, I found completely burnt products of combustion. I have 3 carbon, therefore I have 3 CO2. I have 8 H atoms, gives me 4 H2O. And therefore, the oxygen which I need to carry is 3 plus 2, that is 5. And accordingly, I have 3.76 into 5 moles of nitrogen, and I get in my products, I have 5 into 3.76 moles of nitrogen. Therefore, what is the type of mixture which should be formed such that it is going to be stoichiometric? Well, it is going to be 1 volume of propane divided by 1 plus 5 into 3.76 moles of nitrogen. This is the total volume of the mixture, or rather, when I talk in terms of percentage volume by volume, it is going to be into 100, and this corresponds to a value around 4.03. Or rather, if I were to put in terms of this, maybe I am looking at this around, let us say, 2.2 to 2.3. I am looking at the L value around 9.5. Apparently, I should have formed a mixture in the warehouse wherein the ignition primarily happened after something like almost 15 minutes after release of gas, after the release got started over here. I should have formed a mixture over here which is around 4.03. Now, I want to calculate what is the dispersion, what is the value of the concentration at this point when some mass gets released here. Let us say that the mass which is released in this cloud is something like m dot, or let us say q dot s. This is the abbreviation we are working. You know what happens is the pipeline leaks for quite some time, and therefore, you form this fountain exists for some time, and therefore, this fog is something like a continuous release over a period of time. Therefore, I can assume it to be a steady heat release, so much kilograms per second. Therefore, two things we say, namely at the warehouse I should have formed a mixture whose volume by volume, percentage wise, volume of the propane divided by volume of mixture is 4.03, 1. Second is, we also say that the atmospheric stability conditions on this particular day when the accident happened or when the leak happened is condition F. Therefore, let us come back. Yes, I have the atmospheric condition being F, and therefore, let us see how I should do this problem. Therefore, I tell, well, I am interested in the concentration chi at a distance. We say this distance downhill is 330 meters and it is downhill along the wind. Therefore, I am looking at concentration 330. I am not looking at the lateral direction, it is along the direction of the wind. Therefore, y is equal to 0 on the surface of the earth, that is 0, and this we found is equal to q dot s divided by, I have 2 pi u into the dispersion coefficient in the y direction, dispersion coefficient in the z direction, and if we have a spill of something like it was between, let us say, 15 to 25 meters, something, the spill of a particular height, I take the mean height of the spill is something over here from which the gas diffuses out. I say, well, it is equal to exponential of minus the height at which the effective mass gets released, that is h squared, but divided by 2 sigma z square. This is the way I get the concentration. But before I get the concentration, let us do physically, let us try to understand the problem a little bit more before I use this particular formulae. Therefore, what is it I do? I plot maybe the lines having some concentration as the spill takes place. Let me say, well, the spill takes place over here, corresponding to the place where the pipeline leak occurred. After some time, well, the spill propagates out over here. That means this is the direction of the wind direction is along this. Still after some time, a little bit over here it propagates, and well, it comes over here. This is the way the spill propagates out. And after some time, well, the spill propagates out further, and so on. Maybe after quite some time, well, the spill keeps propagating out because the wind carries it forward. This is the direction of the wind, let us say x, that is the direction of the wind direction. Well, these are the lateral directions. You have the maximum concentration over here, and along the lateral one I can do, and if I want the lateral the concentration maybe at this particular point, all what I say is at this particular station x, wherein I get this value of sigma y and sigma z. At this particular point, I now introduce the value of exponential minus y squared by 2 sigma y squared. I can therefore determine at any concentration, therefore I can determine maybe when the front of the particular cloud along this is here, well, I know that the concentration in this zone is so much. Maybe when the cloud travels forward, the concentration is this, and this is what I want to do. This is where maybe the warehouse is, and this is where I get a stoichiometric value of the mixture as being 4.03 percentage volume by volume, and this is what I want to calculate. And this distance we say is from the source is something like 330 meters, and this is what is given in the problem. Therefore, to be able to get, I'm going to calculate the concentration maybe at this particular point or maybe at this particular point over here, and the lateral ones if I'm interested in some mixture over here, some particular flame over here, we know, well, the flame got formed over here, the dimensions of this building are just a few meters compared to 330 meters. Therefore, I am just looking at the value of concentration at this without any, we are not looking at the lateral dimensions, and therefore, this is the type of concentration I am looking at. Therefore, I have to determine the dispersion coefficient sigma y and sigma z. We also note this atmospheric stability is in an open area. There are not many buildings. Apparently, there are some trees. Therefore, it is as good as in a village, wherein you do not have the high-rise buildings which create eddies and all that. Therefore, I say, well, I need something like a rural surrounding, rural area. Therefore, the value of sigma y and sigma z at 330 meters away, for which I want to calculate, should correspond to a rural condition and not an urban condition, and the steady release is so much kilograms per second. Therefore, I will get the concentration in kilogram per meter cube, right. Therefore, we have to look at the rural for the dispersion coefficient, and therefore, let's take a look at the dispersion coefficients and get the values of sigma as sigma y. Therefore, we go further, we say, well, these are the minimum ignition energies as a percentage of volume of fuel divided by the volume of the mixture. We find, well, propane air has a very narrow range, and the upper range was 9.5, the lower range was around 2.2, well, the stoichiometric is around 4. And when we talk of methane, well, methane has a lower value of the, a higher value of the percentage fuel in the volume of the mixture, but its value of the upper value, U value, is much higher. And if we talk of hydrogen, well, it is even wider. We will do a problem involving hydrogen air shortly. But this is the type, and this is what we are talking of as stoichiometric, and I want to calculate the value at 330 meters, and I want to find out whether stoichiometric mixture is possible. Well, we go to the next one, we look at the dispersion coefficient for continuous release in urban. We said such formulae and figures are available both as plots and formulae. We are not interested in urban, we are more interested in a rural because there are no big buildings. And we also said, well, just now that the atmospheric stability conditions A, B, C, D, E, F, being a cold winter night, the wind velocity being quite low at 2.7 meters per second and not much cloud cover, the dispersion coefficient sigma y is given by this equation, sigma z is given by this equation. Let's calculate these values. Therefore, I now get sigma y is equal to 0.04 x into 1 plus 0.001 x to the power minus half, where x is that 330 meters, and you get sigma z is equal to 0.016 of x into 1 plus 0.003 this is 3 zeros, 30 into 3x to the power minus 1. If I substitute the value of x, because I am interested from the point a distance 330 meters, the value of sigma y comes out to be equal to 13 meters, that is the dispersion, standard deviation, which is the dispersion coefficient. The value of sigma z comes out to be 4.8 meters. Therefore, I am interested in the concentration at 330 meters away. Y is 0, that means I am not looking at the lateral, I am just looking along the wind direction. On the surface of the earth, Z is equal to 0, gives me the value as q dot s divided by 2 pi, wind velocity is 2.7 meters per second, into sigma y as 13, sigma z as 4.8, into exponential of, now you know the mean height of the fountain from which it is coming, let us take it as 12.5 meters, 12.5 squared, into 2 into sigma z squared, that is 4.8 square, and if I solve for this, I get the value as equal to 6.36 into 10 to the power minus 5 q dot s, where q dot s is kilogram per second, and the value of chi at this particular point is equal to kilogram per meter cube. Now, I would like to convert the concentration kilogram per meter cube into volume of fuel or volume of propane divided by the volume of the mixture, and immediately I note, well, propane has a formula C3H8, therefore 12 3s are 36 plus 8 44 gram per mole is the molecular mass, or rather this is equal to 0.044 kilogram per mole, and we know a mole of any substance has a volume at standard condition of 22.4 liters. Here the temperature is something like 0 degrees centigrade, temperature is 273 Kelvin instead of being standard condition being 298 Kelvin. Therefore, if I were to express chi in terms of volume by volume, I get is equal to 6.36 into 10 to the power minus 3 into q dot into, now this is so much kilograms, in terms of mole it is 0.044, and now this is so much moles, a mole of gas contains 22.4 liters, that is 0.224 meter cube per meter cube. I correct for the temperature is equal to 273 divided by 298. This gives me so much volume by volume, and if I want percentage volume by volume, I multiply by 100 and I get the value of concentration in percentage volume of propane by volume as equal to into q dot s, so much kilogram per second, into 100, that is 297, so much percentage volume by volume. Therefore, I find I am able to find out at this particular distance this, and if it is going to be something like 0 is equal to something like 4.03 corresponding to stoichiometry, I can estimate what is the rate of the leak, or if I know the rate of the leak if it is given to me in Q dot S, well, I can find out the concentration here and I can verify whether a stoichiometric mixture is formed at what distance. Maybe at this distance a stoichiometric mixture would have been formed. And therefore, such type of problems we do to estimate the effect of atmosphere in dispersing the gases. Therefore, in such problems we are able to take care of the different conditions of the atmosphere, like a cold winter night, the wind condition, the cloud cover, and solve it using the determined parameters of the dispersion coefficient sigma y and sigma z, which are calculated for the particular atmospheric conditions. Well, this is how we do problems on atmospheric dispersion, and this is how the problem of the case of Port Hudson leak is done. Let us take one more example, and this example is important because it happened in Bhopal, and we call it as the Bhopal Gas Tragedy. You had a tank containing methyl isocyanide gas, isocyanide liquid, methyl isocyanide. You have huge quantity, something like 40 tons of methyl isocyanide, and what happens during the regular cleaning operations, and mind you, the plant was not doing well, there was not much incentive for people to work here. One of the workers, while cleaning the valves, there should have been a hood which protects ingress of water into the methyl isocyanide. While cleaning it, he did not apparently take the precautions, and water sort of seeped into the methyl isocyanide. That means you have hydrolysis of the methyl isocyanide. Methyl isocyanide is CH3 CNO, and it reacts with water in the hydrolysis reaction, that is water, and what it forms is CH3 NH2 methylamine, plus it also forms CO2 gas. Therefore, the act of accidental ingress of water into the methyl isocyanide tank led to generation of carbon dioxide, which is a gas, increases the pressure. This reaction is exothermic, therefore increases the temperature. And also, there were other problems. The tank was not clean, it contained little bit of chloroform, little bit of iron, and therefore temperature started building up. Well, you have the sort of this monomethylamine over here. Maybe it further reacted with the methyl isocyanide to form, let us say, dimethyl urea, and it further reacted with methyl isocyanate to form trimethyl butyrate and so on, but this is the primary reaction. Well, the tank pressure got increased to something like almost 15 bar, and the temperature, because of the exothermicity, increased to something like 200 degrees centigrade. Therefore, it is bubbling over here, bubbling and hot. The gas, something like when you shake a soda bottle, you have the mixture of water and air, that is the two-phase flow coming out. Because of this bubbling over here, the liquid and the gaseous methyl isocyanide get released through a vent valve. And we already told a vent valve, if only gas flow takes place, the rate of mass flow through the vent is small. But the moment you have liquid and gas, that means a two-phase flow through a vent valve, because the evaporation of the liquid over here, it generates a much larger quantity of the vapor of the gas which is being vented out, and therefore you have a large amount of methyl isocyanide which is coming out of the tank in the Bhopal gas tragedy. Well, the accident happened, let us get back to atmospheric dispersion, on the night, almost midnight, 2 to 3 of 1984. I think this is when it happened. Yes, December 2 to 3, 1984. It was a cold winter night, temperature around -1 to temperature around 1 to 3 degrees centigrade. This is the type of temperature. The wind velocity was around 2.9 meters per second, which is a very low wind velocity. And this combination of 2.9 meters per second, not a cloudy night either, gives you an atmospheric stability condition as F, which is extremely stable. And therefore, well, you have the leak taking place over here, methyl isocyanide. You have the wind velocity of 2.9 meters per second. And what it does is, well, just like in the Port Hudson case, wherein you have the propane vapor, well, you have the methyl isocyanate vapor. It drags it along in the wind direction, something over here, maybe with respect to time. It drags it even further, maybe still further. It drags it even further. This is the wind direction, this is the particular source, and therefore maybe you keep on the concentration of methyl isocyanate primarily travels along the wind direction, but it is also getting diffused in the lateral direction, and along the earth you have maybe houses over here, maybe houses over here, in which it enters and causes the particular tragedy. Therefore, I am interested, let us say, well, as an example, let us calculate the concentration of methyl isocyanate. We are not talking of near distances. You know the fatalities in this particular accident are enormous. Therefore, let us calculate at a distance, let us say 3 kilometers away. Let us say downwind 3 kilometers away, and let us now calculate what is the type of concentration here. To be able to know the concentration, I must know what is the concentration, and mind you, you have something like, out of this tank which had something like 40 tons of methyl isocyanate, something like 30 tons leaked out in a matter of something like an hour. Therefore, if I were to say Q dot S is equal to 30,000 divided by 60 into 60, so much kilograms per second is what got leaked out. I know the value of Q dot S, and I want to calculate the concentration at a distance, let us say 3 kilometers away. Therefore, I say, well, concentration at 3 kilometers, let us calculate the mean value, because once I know the mean value, I can always apply e to the power minus y squared divided by 2 sigma y. I can calculate the concentration at this y, and find out what is the region in which maybe the people got affected. Maybe here also people are getting affected. Therefore, the region in which the people got affected. Therefore, at 3 kilometers away 0 0, I write as equal to Q dot S divided by pi u into, I have sigma y into sigma z into exponential the height from which the release takes place, h squared divided by 2 sigma square. Therefore, let us put the numbers down now. We put the numbers. We say sigma y corresponds to the condition f of the atmosphere, and at f of the atmosphere, yes, we already did the propane example at f atmosphere. We know sigma y and sigma z. Now, instead of using this equation, sigma y is equal to 0.04 x into 1 gives me 3 meters, at x is equal to 330 meters. Now, I am interested in 3 kilometers away. Therefore, my x is equal to 3000 meters. Therefore, substituting in the value of x as equal to 3000 and 3000, I get sigma y as equal to 105 meters. So, you find it has dispersed much more, that the deviation or the standard deviation is much higher, because the dispersion is much higher. Sigma z, if I calculate 0.016 x into 1 plus 0.003 x, where x is equal to 3000, the value is 25.62 meters. And therefore, if I were to write the concentration over there, I get concentration at this particular distance is equal to, I already calculated 30,000 by 60 into 60. This number is equal to 8.33 kilograms per second, because something like 30,000 kilograms in a matter of an hour, that means 60 minutes into 60 seconds, 8.33. Therefore, I have 8.33 divided by pi. The wind velocity we said is something like, that night it was around 2.9 meters per second, into the value of sigma y is 105, the value of sigma z is 25.62, into exponential of minus the height of the stack squared divided by 2 into sigma z squared, 25.62 squared. The height of the stack was around 10 meters, and therefore, if I put the height of the stack h square is equal to 10 into 10 is 100, well, this gives me the value of chi, and this works out to be something like 3.15 into 10 to the power minus 4 kilograms per meter cube. Well, a concentration expressed in kilograms per meter cube is a little more difficult to interpret, because we are used to concentration being said as so much parts per million or volume by volume. Therefore, let us convert it to something like parts per million, and we do this by looking at the molecular mass of methyl isocyanide. The molecular mass of methyl isocyanide is CH3 CNO, that is 12 plus 3 plus 12 plus nitrogen 14 plus 16, 16 fours are 30, 42, 45, 45 plus 12, 57, C12, CNO 12, 24, 24, 27, 27, 41, 57 gram per mole. And if I know this is equal to 0.057 kilogram per mole, I have already calculated the value of concentration as equal to 3.15 into 10 to the power minus 4, so much kilogram per meter cube. I want to convert it into, first I convert it into moles, and therefore I divide it by 0.057. This gives me something like moles per meter cube. I know 1 mole at standard condition has a volume of 22.4 liters, and therefore this gives me 0.0224 so much. Now this gives me meter cube by meter cube, but this is at the standard condition. Well, that day the temperature was around 2 degrees, that is around, let us say, 274 degree Kelvin, divided by standard condition is 298. Well, this gives me meter cube by meter cube, or parts of volume per the total volume. And if I calculate this number, this gives me the number as equal to 1.27 into 10 to the power minus 4 volume by volume, or this is equal to 127 parts per million, because million consists of 10 to the power 6, and this is 127. That means in the air at a distance of 3 kilometers away, the methyl isocyanide has a concentration of 127 parts per million, which is quite fatal, which is quite large. And this is the way we look at dispersion of the gas produced in this particular release of gas from the vent because of the high pressure due to the chemical reaction. Well, this is how we calculate the dispersion. Let us do one small problem, because of late we have the hydrogen economy, we want to use hydrogen gas. We have seen these gases, we did not consider much about their molecular mass because they are drifting on the ground. Let us consider a case of a buoyant gas such as hydrogen gas and its dispersion. Well, the type of equations what we use, the way we do the problem remains the same. Therefore, let us consider the specific example of buoyant hydrogen being released accidentally at the rate of 400 meter cube per second from a stack. Maybe there is a plant which is generating, maybe there is some excess hydrogen, maybe it is getting released at this particular rate at some instant of time. Well, the wind velocity on this particular day it is being released is 1.5 meters per second. Now, I want to be able to say, well, this is the rate at which, let us draw this figure, because we know how to draw the release from a stack for a buoyant gas. Well, this is the stack. What is going to happen? Because of the initial velocity effects, well, the gas will move further, and because of the hydrogen gas being lighter, well, it comes over here, it mixes with air over here, and from here the mixed gases, that means the gases due to the initial velocity and the initial buoyancy come to this zone. Over here the wind velocity takes it forward at the rate of the wind velocity being 1.5 meters per second. And what happens? We have a cloud, which is a cloud concentration keeps forming in this particular direction, and maybe it comes at this particular, on the ground level it comes here after some time, or at this particular point we know what is the maximum, and when it's further comes over here, it interacts with the earth, and then I can find out the concentration at any point over here. And this is what I want to do, and therefore I again know, yes, well, my equations are clear to me now. Well, I say concentration at any distance x, at maybe along the surface of the ground y is equal to 0, along the surface of the ground, that means z is equal to 0, along the wind direction, that means along y, that is 0, is given by, again we have, yes, the mass, the volume. Now I say volume is released, q dot s, so much meter cube by second, divided by 2 pi u into sigma y into sigma z into e to the power of minus, I have the height of the stack into 2 sigma z square. Where, in this particular problem, let us presume, or based on the Froude, that a densimetric Froude number, I say, well, the effective height, or capital H, even though the height of the chimney or stack from which it is released is small h, well, the effective height from which it is released is capital H, and we assume that h in this particular problem is, let us say, 10 meters. Well, I can find out the value of chi at the different values of x, for which sigma y is so much, x for which sigma z I can calculate using, and in this particular problem I wanted to do this problem for two specific atmospheric conditions. One, maybe the release takes place on a day in which the wind velocity is small, but it is noon time when I have the sun shining just above me, when it is hot afternoon, fairly still day when the wind velocity is 1.5 meters per second. I want to do the same problem when I have cold night, extremely cold, again there is not much cloud cover, therefore I say, well, in the afternoon, because of the low wind, the atmospheric stability is A, cold night, not much cloud cover, same low wind velocity, well, it is equal to condition F. Therefore, what is it I do? I evaluate sigma y, sigma z at different distances, at the distance of interest, and not only at the distance of interest, but also I sort of presume that for condition A I get this value, for condition F I get these values, and I can compare what is the type of concentration I get on a hot afternoon when the insolation is very high, or on a cold night when I have a stable atmosphere. Let's just quickly put this down. I have the value of chi, which is concentration, is equal to q dot s. I think I already have the formula here, no need to rewrite it. I have chi is equal to q dot s divided by 2 pi u sigma y sigma z exponential of h square by 2 sigma z square. Well, I'm interested in this particular problem at a distance, let us say 1 kilometer away. Well, it diffuses away, it still diffuses away. I am interested on the surface of the earth at a distance 1 kilometer away. At this particular point, therefore, I sort of calculate the concentration at 1 kilometer away, that is 1000 meters. For y is equal to 0, I am just considering along the wind direction, along the surface of the earth. This gives me a value. I'm looking at a number wherein I said, well, q dot s I gave as equal to 4000 meter cube per second, volume is specified, and if I calculate the value at condition A for 1 kilometer, I use the formula given for either rural or for urban area. In this problem, maybe this factory is, or this place where the leak happens is again, let us say, a rural setting. Therefore, I know the value of let us say sigma y. Well, sigma y is given by 0.22 x into 1 plus 0.001 x to the power minus half, and therefore, and similarly sigma z for condition A is given by 0.03 0.20x, and therefore, these are all standard things. These are available in books on atmospheric dispersion, and I calculate at the value of 1000 meters, the value of sigma y comes out to be equal to 210 meters, and the value of sigma z comes out to be equal to 200 meters. Well, I substitute these things. I know the height of the stack is 10 meters. I can find out the value of chi for the condition A. Similarly, I know for condition F in the rural setting, I know sigma y, sigma z. I calculate these values. When you do this, you will find that the value of the chi under atmospheric condition A is very much less than the value under the atmospheric condition, which is F at the same condition. And this is how we do problems involving dispersion of different gases, maybe different explosive gases, ability to form a reactive or a stoichiometric gas mixture, and this is all about the atmospheric dispersion. Well, we now move forward. We have done so far, we have seen a good insight, or we have a good insight into different types of explosions. We said, well, I could say a gas mixture could explode, maybe a dust mixture could explode, and the explosion could come from atmospheric dispersion. We also looked at solid and liquid explosives, and having said all this, but how do we look at the quantification of damages? That is something which we are still to do. Can I say that, well, this explosion will cause, let us say, or my lung to get damaged or my house to fall, and therefore let us take an example. Let us say an explosion takes place, and what does the explosion do? Well, in an explosion you have blast waves which are being formed, and even if I do not have a detonation, a blast wave can still be formed, because if I have highly turbulent combustion, I can still get a somewhat a weaker blast wave. And what does the blast wave do? Well, the blast wave has an overpressure across it. It also has some impulse. And therefore, let us take one look at what are the type of overpressures and what are the type of damages which an overpressure can do. We will just take a small particular example, and we will not consider all the cases. We just consider what are the damages which can take place. And if I were to say, well, overpressure, if the overpressure is greater than, let us say, around 1 kilopascal, well, the glass windows of a building will break. If I have overpressure greater than around 35 kilopascal, well, the eardrum ruptures. We looked at this example. We said, well, eardrum has a very fast frequency response and it just ruptures because of the high overpressure. If I take a look at buildings get damaged, it happens for around 60 kPa. Well, a person gets knocked down when the overpressure that hits him is something greater than 70 kPa. But we also said that it's not only overpressure, the impulse also knocks down a person. Well, our lungs get damaged when the overpressure is 210 kPa. Mind you, we talked of air in the lungs which causes the amplification of the reflected blast waves, and that is what causes the damage of the lungs. And we said if the blast overpressure is greater than around 700 kPa, well, it is lethal, it almost kills a human being. Well, these are things which have been, damages have been catalogued. We say, well, for these things you could get the type of the following quantification of damages. But we all know that when we talk of damages, it's not that, maybe let's go back to the previous one. Well, let us consider the specific case of eardrum rupture. Maybe some people who are very strong and who have better resistance capacity, maybe even at 60 kPa his eardrum will not get ruptured. Whereas a small infant, a child who is more fragile, maybe its eardrum would get ruptured at a much lower value. Therefore, we tell ourselves, well, some people or some buildings or some other objects are more vulnerable to damage than the others. Therefore, if I have this as the mean value at which, let us say, damage takes place, this is the probability distribution function Px is equal to 1 over root 2 pi sigma e to the power x minus mu, where mu is the mean value divided by the standard deviation square. Even though maximum number of people get affected by the average value, there are a sizable people who are more vulnerable. They get damaged when the overpressure is much lower, and there are some people who have much higher resistance. They can withstand a much higher overpressure. And when we say overpressure causing the damage, we can say, well, overpressure is something like a stimulus which causes this. Therefore, we say, well, it is more reasonable that we represent the effect of overpressure, or in this case the stimulus being overpressure, as a distribution like this, wherein more number of people or more number of buildings, and buildings also have some statistics because the material of construction is not the same. There are some dispersions coming over here. Some buildings are more safer, some buildings are less safer depending on the quality of the materials used for construction. Therefore, you have something like a probability distribution, and therefore we say, well, we expect that maybe the number of people who get influenced by a stimulus follows a distribution like this, which is a probabilistic distribution. Having said that, let us go ahead and say what is the stimulus we are talking of. I think here I use the board for a minute before I return to the slides. When I say overpressure, well, it is the stimulus which leads to some eardrum getting ruptured when the overpressure is something like 35 kPa or so. But what is this? This stimulus need not be overpressure alone. Let me take you through an example. Supposing I have a cloud of fire which is formed in an explosion. Suppose I have something like a flash fire, let's say. All of a sudden a fire comes and blows out. That means the fire is there hardly for 0 seconds or very, very short time, in which case maybe the people are not affected by the fire. Whereas if the fire sustains for a few seconds, well, the radiation from the fire is sufficient to cause damage to the human being or to the building adjacent. Therefore, when I take an example of a fire, the intensity of radiation from the fire, I call it as IE, so much kilowatt per meter square, and also the time over which the fire is available, that is fireball is available, should be a parameter, or that should be the stimulus causing damage. That is, the effective parameter causing damage must be a combination of some of these things. Let us take one more example. Supposing I have a spill, that means in a particular case I am releasing carbon monoxide. The concentration of carbon monoxide is, let us say, so much ppm, and if the concentration of ppm is over prolonged duration, well, the effective duration should be concentration into time, because it takes some time for the body to absorb the particular poison, and therefore we say, well, carbon, we expect the effective parameter to be maybe a product of C and T. But if you have gases like ammonia, which are much more harmful, it could be something like C squared T. Therefore, we have to talk in terms of the effective parameter causing damage, which may not be a single parameter like overpressure. It could be, let us say, a combination of, let us say, overpressure and also impulse, such that in the dynamic region it could be a combination of these parameters. And this effective parameter or the stimulus which causes the damage is something which is known as a dose. Therefore, we tell, let's return to the slide. We say that the effective parameter or dose which causes the particular damage when I have a toxic gas release could be a product of the concentration in ppm into time in seconds. If I have something like ammonia gas whose concentration which is a dirty gas, the concentration is more harmful than more effective than the time, it could be C squared T. In case of explosion, if we talk of fatality due to hemorrhage, well, overpressure is a good indic, it's a single parameter. Eardrum rupture, we just now saw delta P. Injury from impact is more from impulse. And what is this impulse? Impulse is Newton second. We talk in terms of specific impulse, ISP per meter square, Newton second per meter square. We talked in terms of glass breakage, again overpressure. When we talk of fatality from, let's say, a fire or a fireball, well, you have something like an effective radiation, i.e., so much kilowatt per meter square. You have effective time, that is effective duration. And it so happens, if I do a series of experiments, I find that the effective parameter or the dose which causes the particular consequence is something like IE to the power 4 by 3 into the effective time divided by 10 to the power 4, where IE is kilowatts per meter square, the effective duration of the fireball is so much seconds. Having said that, well, we say, well, dose is what we call as an effective parameter. The dose causes the adverse influence like damage, maybe death, maybe it can be defined as extent of harm. Well, as the dosage increases or the effective parameter increases, the degree of damage keeps increasing. But it is time that we take a look at what exactly dose does. In 6th century, we had a scientist by name Paracelsus, and he said dose alone makes a poison. That is, the amount of the effective parameter is what causes the harm. All substances are poisonous. That means he says everything is poisonous, including water, because if I drink too much of water, well, I am in trouble. That means all substances are poisonous. There is none which is not a poison. The right dose distinguishes a poison from a remedy. Therefore, we must remember, if the dosage is high, well, I could have the harmful effects coming, and dosage is something like the effective parameter which causes the particular damage. And we already said, well, if I have something like a stimulus, I could have something like a distribution wherein the average person gets affected when the stimulus exceeds some limit. But if I were to take this distribution and take a cumulative value, that means I say Px going from minus infinity, that means I say cumulative distribution phi x is equal to, well, this becomes the value, and this cumulative distribution has a role from minus infinity to increase over here. Well, the person starts getting when the dosage exceeds a value x, because below this, well, the threshold value is so small, nothing really happens. Therefore, the response or the adverse effect starts over here at a threshold value and keeps on increasing as the dosage increases. The shape of this curve is a sigmoid shape, and such type of curves which tell you the effective parameter, how it causes the response or how many people are affected, is known as dose response curves. Let's take a look at one last figure. That means if I have a dosage which causes maybe, let's say, human beings to be killed, we call it as a lethal dose. Maybe for dosage exceeding this limit, maybe people start getting affected. Maybe on an average, this is the lethal dose. Maybe all types of people, all people are apparently killed when the lethal dose gets over here. This is the cumulative distribution, which we said has a cumulative distribution index or something like a sigmoid shape. The point where 50% of the objects or 50% of the people are affected is known as lethal dose 50, it's known as LD50. So also maybe this is for lethal dose, maybe I could have an injury which people can recover, we say is reversible. When it is reversible, we say effective dose, and effective dose will be less than the lethal dose. Well, I have a cumulative distribution like this. When 50% of the subjects get affected, I say, well, it is effective dose or ED50. In between the effective dose and lethal dose, I could have something like let us say a toxic dose wherein people are affected, the case is irreversible. I say it could be toxic dose and I could have a TD50. We will continue with this, the response curves for dose and response. We find that the curve is sigmoid or non-linear, and we will try to apply a linearized form of this curve known as a probit to quantify the damages, and this is what we do in the next class. Well, thank you.